Okay. Hi everyone. We're going to start now. Thanks for coming. This is your midterm crash course for ELEC1111 run by ELSOC, the Student Society. My name is Laith. I'm one of the directors for ELSOC, and I'll be running this seminar with Otto, and he's one of the executives. Please, if you haven't already, please scan the QR code and get your attendance in. It does help us as a society for funding from ARC. I'll give you guys a few seconds to, if you haven't already. Yep. Let's have a look. We've also got, if you might be interested in joining ELSOC, we have our subcommittee recruitment that's been open for about 2 weeks now, a bit close to that, and it closes around early next week. So if you're interested, you might want to scan that, and if you're interested in applying and joining us, and creating these resources, but also creating events around electrical engineers. Without further ado, I guess we'll just start with the crash course. So for your midterm, you'll be covering 4 main topics. So you start off with circuit basics, then you go through your Kirchhoff laws, and then you do your circuit theorems, so Thevenin and superposition, and then you go a bit into steady state responses for capacitors, and so you'll see that later in this crash course. I'll be taking the first 2 topics, and then we'll switch over to Otto for the next 2. So just quick introduction. So yeah, that's pretty much just what I said. The key takeaway from this crash course is trying to build confidence in answering questions, especially for your midterm. You often find that the hardest part of answering questions for the midterm is actually setting up the equations as opposed to just computing them. So it's good to understand how to solve these questions and sort of like the rationale about how you think when you're solving these problems. And so I'll be a thought process when I'm answering these questions to help you out. We'll be covering a lot of past paper problems. So you might have, if you've already done the past papers, you've probably seen some of these. There are some questions that we also come up ourselves, which have small like tricks in them, or they're kind of a bit difficult in different ways, and that's just to help you sort of get ready for like unexpected situations, essentially. So we'll start off with circuit basics. So this is our first topic. Just a bit of theory. These are like the equations and a bit of theory you have to understand for the first part of the course. You can find most of this on your formula sheet, but it's just good to know. The last 2 are sort of extensions of equivalent resistance, or resistance in general. But yeah, I guess another one that might be useful that isn't actually included in this would be the definition of power. Your lecture notes, you should know that power is equal to the change in energy, or it's equal to the rate of flow of energy. And so that might be useful for one of the questions we will go through later. But yeah, that's pretty much it. If you understand all of this, you'll be pretty set for the first topic. And so we'll start off with question 1. This question was taken from the 2020 paper in term 3, and it was question 1, so it's the first question. A lot of the past papers start off with questions of equivalent resistance. And so in this problem, what we see is that they're asking, in the figure below, calculate the equivalent resistance REQ as seen from the terminals A to B. So we're looking at this right here, and we're trying to find the resistance between these 2 terminals right there. And so what we want to do, essentially, is simplify the got to fix that a bit. We want to simplify this giant network of resistors into one resistor, just like this. And we'll call this REQ. And so what we can do is that we can start simplifying these resistors in parallel and series. So what we can see is that if we look at this figure, there's some resistors that are kind of, they're sort of connected in really weird ways, especially if you've seen this wire right here. It makes things very difficult at the start because nothing is obviously connected in series or parallel. And so what you want to do is, instead of just looking at what's the sort of like obvious indicators of a parallel or series connection, you have to go back to the definition of what parallel and series. If you think back to your lectures, it probably was mentioned that parallel elements are connected at two nodes. So if you have a node here and a node here, if you connect two resistors this way, you know they're in parallel because they share two nodes, these two. And similarly, if you connect two resistors, but they are just connected by one node, that's series. So this would be series, and this would be parallel. Oh, that's a bit. We'll see this a bit in this problem, but more so in one of the later problems. Additionally, you might also know that when we do have resistors and they're connected in parallel with a wire with no resistance, then we have a short. And so what happens then is that the resistor is essentially bypassed. So if we have something like this, we have a wire through there and a wire through here, this resistor right here is essentially nullified because all of the current, if we say that this is current I, all of the current I doesn't divide between these two components, all of it goes through this side. So this resistor right here becomes essentially useless. And so that's going to be what we'll exploit for this problem here. So the first thing that we can observe was this wire right here, just around the middle. What you might be able to see is that this wire connects, well, essentially one node really, and it connects from right here, and it comes both nodes on opposite sides of this 10 ohm resistor. And so as a result, this is essentially a short circuit, and so this resistor is bypassed. As a result, we can sort of redraw this middle part right here, just this part. If I just put an arrow, this part essentially just becomes, if I make this the 3 ohm, this becomes the 2 ohm resistor going down, and this becomes a 4 ohm resistor going down. So this is 4, this is 2. Oh, this is very messy. 2, and that's 3, and then we connect these two, and then that becomes the 4. And so now this is a bit more clear about the sort of so now is that these two resistors right here are in parallel. So what we can do is that we can simplify these two resistors in parallel, like so. And so what we'll do is I will do 4 parallel 2, and we can connect that 4 parallel 2 in series with the 3 ohm resistor. And then we have this other resistor, this 4 ohm resistor, that's in parallel with all of what we've just talked about, the 3 ohm resistor and the 2 other resistors in parallel. So it would say that these 3 resistors are also in parallel with the 4 ohm resistor. And this is then in series, so if we simplify all of that, this is in series with this resistor. So this is 4. So let's write this a bit like nicer. Four parallel, and this would be 3 plus 4 parallel 2, and then yeah, that looks about right. and then we just add 4. And that would be our REQ. And so you can sort of substitute this into your calculator. Yeah?
I just have a question. Can you just explain again why the 10 ohm resistor is like we won't consider them?
Sorry?
Why is it a short circuit?
Why? Because both of its nodes are connected by a wire with no resistance. So if we have a look here, this is, use this marker, this is one node and this is another node. And so we see that we have this resistor going through here, but we also have this wire.
So because it's connected at 2 points on the same wire. And when would we consider it? Like when would it not be a short circuit?
When would it not? Well, when you don't have a wire. So if this was not connected here, so if you had maybe another element here, for example, this wouldn't be a short circuit, because then you would have one resistor here going down that way, and then you have another resistor around here, and so this would be 2 resistors in parallel. Hopefully that sort of cleared up your problem. So yeah, I won't compute this right now. It might be a bit tedious, but it's fairly straightforward, hopefully. All right, we'll move on to the next question. All right, so this question was taken from the diodes. They act a bit weirdly. A lot of students have difficulty with them, so hopefully this gives you some good practice with them. So this problem starts with the circuit in the following slide presents a caravan with a solar panel. So it just describes what the system is. It says that the diode has a forward voltage of 1.7 volts, and that's fairly standard. You'll see that in a lot of problems. Now, do not assume that. Some questions might give you 2 volts, they might give you more than that, but in general, diodes do have a voltage drop of 1.7 volts. And so what the question asks first is that we want to calculate the current I flowing through the battery during the daytime. And so the battery, what we defined as the battery is this dotted line, this section of the circuit right in the middle. So in order to find this, because we have 2 amp source and we've got this voltage source, what we would have to do is that we have to use one of our analysis methods. Now that's actually in topic 2, but you also find that a lot of the problems in topic 1 need topic 2 theorems in order to solve them. So they're sort of like merged together, essentially. So we'll have to use either we could use superposition, or we could use nodal analysis or mesh analysis. In this problem, what you might see is that we have essentially 1 amp, this one current source and this resistor in parallel. And so if you've done source transformation, what you might see is that you could actually simplify this and turn it into a voltage source in series with a resistor. And so what that does is that it sort of eliminates this mesh. I'll redraw it right here for you guys. So if this is the circuit, we can turn that 24 ohm resistor in series with the other 0.1 ohm resistors. And so what we get is this would be a 24.2 ohm resistor. And so this connects this way. And then then the battery comes down that way. And we have our other voltage source. So we turned the current source into a voltage source, so now we have 2 voltage sources. And then we have this resistor, we have that resistor, and we have the diode down here. Oh, got it the wrong way around. So it'd be this. And so what makes this 2 equations, so it makes things quite efficient. So in order to do source transformation, we should probably get the numbers. So this was 12 volts. We've already done that. I'll just translate that over to this diagram. We'll call this is 12 volts. This we said was 1.7 volts. This is 6 amps. This is this is 6 ohms. This is 0.3 ohms. This is 0.2 ohms. And the voltage source, well, because we know that V is equal to IR, we know that if we take the current source that we had, so this is 6 amps, and we multiply it by the resistance, that's the voltage that we would get from the voltage source. So this would essentially be 6 times the resistance that we had was 24 in parallel, and so that would be, there is my calculator. I'll just use this one. Whoop. And so that would be 144 volts. Now, if we use mesh analysis, so we can call this mesh 1, this is I1, and we'll call, well, it's not much space, this is I2. And so we can use mesh, we can create our mesh equations, and then we can try to find I battery in terms of these mesh currents. So, what we do is that for mesh 1, let's say for mesh, let me get some space. Let's do this in black. For mesh 1, we know that we apply KVL to the first mesh. We start, let's just say, from the bottom left. So that would be minus 144 volts. And this, we would add to that, we would have the voltage across the resistor. So this would be 24.2 I1. And then after that, we would have the current going in the middle between the two meshes, but that would be the subtraction of both the mesh currents. So we'd have 0.2 ohms multiplied by I1 minus I2. We say that because I1 here is going down and I2 is going up, and the net, sort of like the net current that we're looking at, is going down. So we'd subtract I2 from I1. Then we have the 12 volts, so we add 12, and then we come back around, and then we mesh is 0. So that's our first equation. Then we can have a look at mesh 2. So from mesh 2, we can start from here. So this would be negative 12 volts, and then we go up, so this would be 0.2. Now in this case, we do I2 minus I1. This is the opposite, and the reason for that is because we're going up I2 and we're going down I1, and so the superposition, essentially, the superposition principle essentially states that the net go, or if you subtract them, you get that that current that we want. So that's 0.2, and then we add 0.3. This one's quite nice. Is 0.2 or 0 plus 6 times I2, and then the voltage across that diode is just 1.7. So that would be our second mesh. Now, what we actually want to find in this problem is that we want to find the current through I battery. And so what we can see from the diagram is that I battery is the current going down through here. And so we can define that essentially as I1 minus I2. So that would be I battery is equal to I1 minus I2. And so we simplify this. So we have to take these equations and solve them simultaneously in order to subtract them to find I battery. So if I do that right now, I would get 24.2 plus that. So from 1, we can say that for I1 we get 24.4 I1 plus, and then for I2, that'd be negative. That'd be negative 0.2 I2. And then we would have, this would be equal, if I just move the normal voltage terms, I would make that equal to 132 volts. And then from 2, that we would have minus 0.2 I1, and then for I2 we'd get 0.2 from the second product, and then we would get plus 0.3 and then plus 6, and so that would give us plus 6.5 I2. And then for the other voltages, so we'd get 12 minus 1.7, so if I just move them to the other side, what we'd get essentially is 10.3. So these are the two equations. Let me clean this one up a bit. And so solving them, what we get is that we multiply this equation by, so it's 24.4 divided by 0. So we multiply 0.2 times 122, we get what we multiply this equation by 122 overall. We get minus 24.4 I1, and then this would be plus 122 times 6.5, so this would be 793 I2, and this would equal to 122 times 10.3, and this would be 1056.6, and so we would add them together. We would add this equation with this one, and so what we get is that these two cancel out, and so we're left with 793 minus 0.2, so this would be 792.8 I2, and that will equal 1.3 plus 1256, and that will give us 1388.6, and hence I2 is going to equal that divided, so we just divide across, we would get 1.7515 blah 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 amps, and so that would be our first current. Then we have to find I1. So I1, if we take this value right here, we'll call this 3, and we put 3 through equation 1. Actually, that's equation 2. Oh, we can use equation 2. Put it through equation 2, we can find I1. Let me get rid of that. That's not what I wanted. We'll just put it. Well, actually, we'll put it through this. And so what we get is that I1 will equal, if I just rearrange it a bit, we got 132 plus 0.2 I2, and then I divide that by 24.4. And so if I just plug that into my calculator, times 1.7515, that was a 2. And then I divide it by 24.4, I get 5.424. And so I battery is equal to I1 minus I2. And so that would be just those two values subtracted from each other. 1.7515. 0.6727 amps. I'm just simplifying it to a lot of significant figures. For your answers, you should aim for at least 3 for your problems before the final answer, and then for your final answer, you might want, you want 3 decimal places for all your problems before the final answer, and then you can simplify to 2 decimal places. And so that's part 1. It's a bit lengthy, but we got there. It wasn't too difficult. Right, so that was part 1. Then, now we've got part 2. And so for part 2, we need to find the total power of the battery system during daytime. So the battery system is right through here. And so we have to find the power through both of these components. So both the resistor and the voltage source. And so what we do is that for question, or part 2, go to the right here. For part 2, we'd find that if we want the power through them, we'd get the power through the battery would equal, it would be the power through the resistor. So P resistor plus P of the 12 volts. Now for the resistor, we know that the power through it is going to be the I battery squared times the resistance, which is 0.2. And then for the power through the voltage source, that would be it would just be VI. And so we know I is just the battery, I battery, which is what we found. And then V, right, 12. But as you, yeah, it would be 12. And so we just substitute those values in. So we would get, if our I value was 3.67, for instance, so 3.67, we would square that, and then we'll multiply that by 0.2, and then we'd multiply 12 times 3.67 again. And so what we'd get is that the power would be 46.733 watts, and this would be power dissipated. And the reason for that is that resistors only dissipate power. So this only dissipates power. You can't really generate power from a resistor. And then for the voltage source, because by the passive sign convention, we say that it dissipates power. It doesn't generate it. So that's part 2. And then for part 3, so this is the last part of this problem, we have to find the total energy absorbed by the LED light over a period of 30 minutes. So the total energy absorbed would be, so it's going to be the power through this. I'll get to that. So we have to find the total energy going through the LED light, which is that system right there. So what we can do, given what I sort of explained earlier, it was this equation right here. We know that power is sort of the rate of change of energy. And so what we can do is that if we take this, we can find the energy from integrating power with respect to time. So if I go back down, if we want to find the total energy through the LED light, we should first find the power. Now, the power is quite similar to, you can derive it in a very similar way to part 2. So the power, I'll just say that that's going to be the power of the resistor, P resistor, plus P diode. And that's going to be equal to, so the current through this mesh, as we found earlier in part 1, is I2. And I2 is going to be 1.7515. I'll just put a reminder right here, just so I don't forget. 1.7515. And so we get the P resistor, which would be times the resistance, which would be 6. And then we get the power of the diode. We have the voltage, it's 1.7, and we multiply that by the current flowing through it. 1.75, 1.7515. Yep. And so we got this from VI. And so if we compute that, we get 1.7515. We square that and multiply that by 6. Ooh. That's not what I want. Times 6 plus 1.7 times 1.7515. And so we get a power of 21.38 watts. And this would also be dissipated. But that's not what we actually want for this problem. What we want is the energy. And so we find the energy. For this integral, what the question tells us is that for this problem, we want to find the energy absorbed over a period of 30 minutes. So we can say that the period is going to be 0. The upper limit is defined for seconds. So that would be 30 minutes times 60 for seconds, and that would be the amount of seconds that we have. So this would be equal to 30 times 60. So at the upper bound, it would be 1,800. Lower bound is 0, and then bottom bound would be, the actual function would be this. And so we just sort of solve this integral. We understand that if we integrate a constant, we get a linear. And then we just substitute those values in. And so what we get is 1,800. So that's going to be 38,484 joules, or 38.4 kilojoules. And so that's the answer for that problem. That's question 2. That should be it. Whoa. Hello. There we are. Pretty lengthy problem. This problem, I believe, accounted for maybe close to 30% or 30 marks. So it's quite a lot. It's quite lengthy, but it's fairly straightforward if you know how to go about answering it. All right, for the next problem, this is another resistor network problem. This is from the 2019 paper. This is from the term 3 sitting, and this was question 1. And so you see that just like earlier networks are usually answered early in the exam. So you've got, most of them are question 1 part A. Right, so for this problem, we have to find the equivalent resistance REQ as seen from the terminal AB. So we'd have to essentially just simplify this whole network right here. And so this is ignoring, obviously, the source. So it's just looking from the terminals A and B. And then using this for the second part is that we have to find the current. And so that we can kind of see that similarly to the way we did the first question for that problem, the way we would do it is that for the second part we have this source, 10 volts, and so if we this network, we should get an REQ, and so I1, it's just I would essentially just equal, we just know our Ohm's law, so it would be I is equal to V on R. So it would be 10 on REQ. So in order to find the second part, we just need to find the first part, which is REQ. So given this network, I'll just redraw it. So what we have, and I'll disregard the voltage source. So this is terminal A. This is a 1 kilo ohm resistor. And then there's going to be this resistor here, this resistor there. Surely I should write it on that side. That's probably be nicer. There we are. Got a bit more space. So that's A, that's B. This would be this resistor there. I can simplify these two resistors in series already. You just sort of see that they are connected only at one node. So I can just sort of do that right now. This would be 3 kilos, this would be 1 kilo. This right here would be 1.5 kilo ohms. And then we have, we've got these two resistors. And so we can see that they both share 2 nodes. And so they're connected in parallel. And so we can sort of simplify that from the get-go. So we can say that we can simplify the 3 and 6 ohm. So if I formula from the formula sheet, we would get the equivalent resistance is 2. So we would get 2 kilo ohms through there. So that's combining these two. This becomes 2 kilo ohms. So this is 2 kilos. And then what we also find is that these two are also in parallel. It's getting a bit messy, but these two kilo ohm resistors are in parallel. Neat trick. If 2 resistors are in parallel and they have the same value, the equivalent resistance would just be half. So you've got 2 kilo ohm resistors in parallel. The equivalent resistance between these two would just be 1 kilo ohm. Hopefully, in your midterm, if you're given nice numbers, you can probably save a bit of time by just knowing that small fact. And so this 1 kilo line of this one wire that connects sort of the B terminal. So this is A. Oh. This is B. Oh, sorry, that's A. This is A, and this is B, and so we need to connect these two. Now, we've already simplified a lot of these resistors in parallel and series, but now we're sort of a bit stuck. None of these seem clearly, yeah.
Why do we have to draw that wire since no resistor or element was connected to the wire?
Sorry?
The last wire you joined.
Yeah.
No element is on that wire, so why is it separate?
That's the thing though. There's no element on that wire, and we'll see that because it's a short circuit. I'll just get through it in 1 second. Any other questions? Yeah, so it was a good catch. That wire doesn't have any. Now that element, oh sorry, it's not a short circuit. Hold on 1 second. This wire essentially connects this node right here. Oh, I did not want to do that. There. This wire connects this node to this node. And so while there isn't any elements on it, what we can see is that if we look at these 2 resistors, they share this node right here, what I've just drawn in blue, and they also share this node. So that means they're in parallel. Even though it's not very clear, they are in parallel. And so that's one of the tricks that you'll find in these sort of problems.
But wouldn't it just not go through those resistors at all?
What do you mean?
Wouldn't it just go through that one wire with no resistance on it?
But no, because what happens is that this wire right here isn't a short circuit. It's essentially just one node. It's a bit hard to sort of visualize, but if you had sort of current going through here, right, it would come down, let's just say it would come through here, and then, ooh, that's a bit weird. You just go by the definition, essentially. That's the best way I could really put it. Because you have these 2 resistors, and they're both connected at 2 nodes. And so, in essence, you'd have to solve these in parallel. So what you'd do is that you'd get 1 on 1.5 plus 1. And so you'd get 0 point Ks. 0.0, so it would be 600 ohms. So we simplified this just a bit more. What we would get is that those 2 are in parallel. And so we get this 1 kilo ohm resistor, and then we would get this 1 kilo ohm resistor, or this 2 kilo ohm resistor. This is 3. And then what we would get is that we would get this resistor here, and then this would be the terminal B. Nope, sorry. And so if that's going through there, that's connecting this. I'm fairly sure it is. Is it not?
So, just to jump in, and it was a really good question. Current would short between there and there. It was a very nice spot, and that actually tells us that this B, this node, is that entire thing. And so our connection is over here.
Oh, you are. Yeah, sorry about that. Let's mix it up. And yeah, and then that would be 0.6. Or that would be K. And so these two are in series, and then that would be in parallel with this, and this would be in series with that. So what you would get essentially is a REQ. 3 kilo ohms parallel 0.6 kilo ohms. Oh, sorry, it would be in series. And this would be in parallel with the 2K. And then you would add all of that to the 1 kilo ohm. And so if we simplify that, we would get 3 plus 0.6. And then that would be 3.6, so that would be 1 on 3.6 plus 1 on 2. So this would be equal to 1.2857 plus the 1k ohms. This is also k, 1k, and then this would be equal to 1k. 857k ohms, and that's REQ. And so for the second part, we take this value right here, and so it would make 10 divided by 2.2857k, and so that would be 10 divided by 2.287257 times 10 to the 3, and that would be essentially 438 milliamps. And so that's this problem. And that would be the current. And then we've just got this last problem. Should probably move a bit quicker. So answer it, but I sort of go through how you would solve it. So for this problem, we would see that it's stipulated that the current that flows through each diode can't break or can't go over 50 amps. If the current goes through any of these diodes, so these are the diodes, is more than 50 milliamps, then what we say is that the diode breaks, and so the voltage across it becomes 0. So what the question asks is that determine which LEDs will light up. We have to find which LEDs will light up. So what we can say is that looking at this node, this is 3 volts. That means that across these 3 up here, they all have 3 volts. And we can say that down here, this is ground, so this is 0 volts. If we just do, we can just check the voltage difference. So moving down this first diode right here and the diode down here, what we would get is that we would get 3 minus 1.7, So this would be 1.3 volts, and this would be 1.3 volts. Up here, this would be 1.7 volts if we declare that this is just ground, right? So this is just the same as that. So, as a result, what we can say is that let's have a look at these first two diodes right here. So, these two on the left. What we can say is that we have enough voltage to go down the first diode. We have 1.3 volts above it. And so as a result, there's not enough voltage for there to be a current going down this way. So it wouldn't be forward biased. As a result, this diode, this second diode right here, would have a current going through it of 0. So I would be 0 for this. And so this would become an open circuit. Now if this becomes an open circuit, then this also becomes an open circuit because they're connected in series. So both of these diodes would in fact not light up. For this diode, we have the voltage drop across that, so it would be 1.7. That means at that node below it would be 1.3 volts. So the current flowing through this would be essentially I equals V on R, 1.3. And then we divide that by 50 ohms. And so that's the current going through this right here. And so as a result, we can find the power for that diode by doing V times I. And so that would be 1.7 times the current, which would be 1.3 on 50. And so I could calculate that actually right now. It'll be fairly simple. And so what we'd find is that the power dissipated by this diode would be this many watts. And so that diode would light up. So these two diodes don't light up. This one does light up. Even though I moved the diode to the bottom, we can sort of work from ground up instead of from the 3 volt potential down. And so what we would get is that the voltage across that resistor right here would be 3 minus 1.7. So we would get V across the 1 ohm is going to equal 3 volts minus the 1.7 volt. And that would be equal to 1.3, which is similar to what we got earlier. And so the current going through it would be I through the 1 ohm resistor would be V on R, and this would just be 1.3 amps because the resistance is 1. And so in a similar way, what we can do is that we can find the power through this to be equal to power is equal to 3. Oh no, sorry, that would be 1.7. Oh, but then also times 1.3. And so that would be 2.21 watts. But the problem though is that if you, I did actually miss it a bit earlier, but even though we did find this power, the question stipulated that the maximum current that could run through that diode is 50 milliamps. And so as a result, the power that actually runs through this this diode is 0. And the reason for that is that I was actually 0. So my bad, I actually moved a bit too quickly. What happened is because we've kind of surpassed the current threshold. And so we get 0 times 1.3 amps, and so the power would be 0. And so that diode would not light up. So this one down there wouldn't light up. So it's only the middle one that would light up. And so that's that question. Any questions about that one? Or yeah.
Is it just zero because it assumes that like the LED would just break? So
Yeah. Essentially. The only reason that last one doesn't work is because of what the question said. If the max current was higher than 1.3, then you would have a voltage drop across it, and so you'd have power through it. It would light up. Right. So now we're moving on to Kirchhoff's laws. Main content points really. It was just KVL and KCL. So KVL around a loop. So you're adding up all the voltages and they should equal 0. And then you've got KCL, which is adding up all the currents that go into a node. And so those should also equal 0. Or you could do the currents entering a node should equal the currents exiting a node. And then you can also do voltage division and current division. You can derive those from KVL and KCL. A neat trick is that if you do only have 2 branches, you can simplify the current division formula by taking the resistance of the other branch. So if you have 2 resistors, R1 and R2, and you find the current through R1, you can take the resistance of R2 over the sum, and that will give you the current through R1. I guess we'll just get straight into the questions. So this is the first problem. So what it asks is that we need to calculate the current and power of the independent voltage source. So it would be this voltage source, and hence find the voltage V1. So it would be this. Now, what we can say is that if we want to find the power through this, voltage source, we have to do P is equal to VI. And so because we have V, we have 3I, we just have to find the current coming out of the source. Now, in order to find the current throughout the source, what we can do is that we can simplify this entire network of resistors and turn it into one REQ. And so in doing that, we can just do V equals IR and then find the current, and then we can find the power. So if you just have a look, this network is a bit simpler to solve than the others. What we can see is that these 2 resistors are in series, so we can group these together. And then these 2 are also in parallel with the 4 ohm, and that's also in parallel with the 3 ohm, and that's also in parallel with the 6 ohm. So these all combine together. So all of these would combine together, and then would add the 2 ohm resistor in series. So if I represent that mathematically, so let me just get rid of all these scribbles. We would get that the REQ would equal, so we would get 7 plus 5 parallel 4 parallel 3 parallel 6. We just add 2. And so you just sort of plug this into your calculator essentially. So you get 7 plus 5, that's obviously 12. And so we'd get 1 on 12. We'd have to use, because we have more than 2 branches, we'd have to use the generalized formula. And so if I plug that into my calculator, what we would get is that we would get 6 on 5 plus 2. And so this would be equal to 16 on 5 ohms. Now that we have REQ, that would be 3 on 16 on 5. And that would be 3 on 16 on 5. That would just be 15 on 16. which is about 0.9375 amps. So that's the current, and so P equals VI would equal to 0.9375 times the voltage, which would be 3, and that would equal 2.8125 watts. And this would be the power generated by this voltage source. It's the only source. If we say that the current, or the passive sign convention, more rather, the current's coming up through here, it's going through the negative terminal, and so we can say that power is being generated. Right, so that was the first part. Then we have to find VI. So now we've found the current going through the voltage source, and so that's going to be, so we know that I here, I is equal to 0.9375, and so what we can find is that the current through I right here is the same as the current going through this 2 ohm resistor, so this is also I, but then I splits at that node over there, and then it recombines over here, because here it's also I. A little bit of current going down this, a little bit going down there, a bit going there, and a bit going there. And so we can use current division. So what we can say is that the current that we actually want is this one. We want the current going down here, and we'll call this I1. The reason why I find the current here is so that I can find the voltage V1. So what we can do is that we can divide it. So we'll do I1. So we'll do I1 is going to equal, essentially, it's going to be using the current division formula. So we would get parallel 3, parallel 4, and then this would be in parallel with the 12, and we'll divide this by 12, and we'll multiply this by I, which is what we found earlier, which is this. So if I just plug that in, 1 on 6, plus 1 on 3, plus 1 on 4, plus 1 on 12. And that'd be divided by 12. And so I'd get 0.1 times I. And that would be 0.1 times I would just be 0 of what we found earlier, which would be 0.093. But we don't want to find the current, we want to find the voltage, V1. So what we would say is that V1 is equal to I1 times R, which is 5 in this case, which is from here. And so as a result, we get 5 times 0.0937. So that would be equal to 0.4685 volts. And so that would be the answer for this problem. Any questions? Yeah?
Oh, no, sorry.
No.
Just tricky.
That was a while ago. That was one we answered. The next one is a question from the 22 paper. And so this is just a nodal problem. This one's actually quite nice because they don't want us to solve the problem. It's just set up the equations. We've already given the nodes that we want to work with. We want to work through we want to work with nodes V1, V2, and V3. So what we do is that we can analyze them. Now what we can see from the get-go is that from V1 and V2, we can see that these two together form a supernode. So that's minus one node to analyze, but it also has another constraint equation. So what we can say is that V2, or we can say that V2 minus V1 is equal to 3. And that's our first equation that we can use. Then we have to analyze the supernode itself, so the currents going through it and out of it. And then we also have to analyze V3. So let's just look at this supernode right here. So we would find that, let's just define some of these currents. So we'll define this current to be going down this way. We'll find the current going down this way. This current's going this way. This current is going this way. This current's going this way. We can't really say much about the current. I mean, we know the current is going this way, but we can't actually quantify what the current is going through the supernode. So from the supernode, what we would find is that we'll call this I1, this is I2, this is I3, this is I4, this is I5. So from the supernode, we can say that I1 plus I5 will equal I2. Now we have to decompose these currents. So we know that I1 is going to be V3 minus V1 on 2 ohms. I5 would be V3 minus V2 on 9 ohms. I3 would be, well, we know what I3 is. It's already given by that dependent current source. It's 4 VO. So we just say it's 4 VO. And that will equal I2. And that's going to be V1 minus 0, because it's connected to the ground right here. So it'd just be V1 in terms of the node voltages that we want to work with, so we can derive VO. Now we know that VO is defined from this resistor right here. And so what we can say is that VO is V3 minus V2 if you take into account the polarities. So VO, oh, that's not the color I wanted. Actually, no, it is the color I wanted. This would be V3 minus V2. And so you can essentially sub that in. And so that's our equation 2. Call this equation 2. Now we only have to create one more equation. We've got 3 unknowns, so you should find 3 equations. So from node 3, we can look at the currents. So I1, I5, and I4 are all moving outside of that node. So we can essentially add them up, and it should equal 0. So for I1, it's the same thing. It would be V3 minus V1 on 2, plus it would be I5, and I5 is going to be V3 minus V2 on 9, and this would be V3, and then I4 would be V3 on 7, and that would equal 0. And that's our third equation. Now, you've got these 3 equations. All you have to do for this problem is essentially just simplify them. You probably want to give them in the form of plus CV3 is equal to D. If D is some sort of constant, it could be 0. And so you do that for all 3 equations, and then that's the answer for that. I won't spend time solving it or simplifying it. I think you guys understand how to do that. Are there any questions about this problem? Yeah.
How do you determine which way the current flows in the most right node?
The most right one, the V3 one?
For I4, how do you know that one gone down? How do you know I1 gone up?
You don't. You just say they are. What happens is that when you set up these equations, they have to be consistent between all the different nodes. So what you can do is that you can just define them. Or say, oh, this one's going down, and this one's going up, and this one's going left or right. And so when you're doing that equation for that node, you'd take that convention and you'd use that for another node. Now, if it just happens to not be in the right direction, then you just get a negative. So you'd get a negative current or a negative voltage. And so you just flip it. Does that sort of make sense? Yeah.
Where do you get the question?
Where did I get this question?
Yeah.
This one was
Are we able to get these ones?
these slides.
Yeah.
Oh, I can. We can probably publish them.
Well,
potentially.
everything's recorded. You'll be able to see the question.
You'll be able to have a look through them. But if you want to look at the question itself and the actual worked solutions for it, it's from the 22 paper. It was term 3 and it was question 2b.
Which you should have access to by now.
Yeah. And so that's this problem. The next problem is quite similar. We have to use mesh analysis. So it's sort of like parallel of the last question. Now we want to use mesh analysis and make our mesh equations instead of the nodal equations. They've already defined the meshes for us, so all of them are already going. So we've got I2, I1, and I3. And so what we have to do is that we would have to apply KVL across the loop, or around the loop, and then from that we can sort of solve these mesh equations and we can sort of decompose them. So if we look at the first thing that we can see, essentially, is that between I2, so this node right here, or this mesh right here, and this mesh right here, we've got this dependent current source. And so what this tells us is that this is a super mesh. And so as a result, what that means is that we know that I3 or I2 minus I3 is going to be equal now. If we want to analyze this, what we can do is that we can, because we have this super mesh, we'll have to look at this bigger mesh. But we still have these meshes inside of them in order to get our equations. And then we have this one that's a bit standalone. So this is equation 1. For equation 2, what we would do is that we can start from this node right here, and then we go clockwise. So we'd say that from supernode, or super mesh, mixing up my words, we can say that we've got 100k, or so 1k, sorry, 1k ohm, and the current going through that would be I2. And this is just the voltage across that resistor, if you're not familiar. So it would be. So that's the first one. And so we go around clockwise, then we hit the voltage source. So we'd get plus 5 volts. And then we'll come back around, and then we would get plus 5k ohms. And then because I3 is going up this way, and I1 is going down this way, we can say is that we can do I3 minus I1. And so from there, then we can continue going around, and then we hit the voltage source, and that would be minus 3 volts, and that would equal 0. That's our super mesh. And then from mesh 1, so it's just a standalone mesh. This node right here, and then we would go clockwise. So this would be 2k multiplied by I1, and then we go through that voltage source. So this would be plus 3 volts. We're going through the positive terminal, so it would be plus. And then we go down the 5 ohm. This would be 5 kilo. It would be 5 kilo ohms. And then we've got I1 going down, and we've got I3 going up. And so as a result, we would get I1 minus I3. So this would be the opposite polarity. And then that equals 0. So we have our 3 equations here. Now we have for the first equation, we have a variable IB. And so we have to define that for our circuit mesh currents. Is running through this 3 volt source. And so as a result, we can just say, if I get rid of some of this clutter, we can say that IB is going to be, that's I1. This is I2. We know that IB is going this way, so we can say that IB is equal to I1 minus I2. And so from this, we would get essentially I2 minus I3. That was just the first part, and it would be 100 times, what was it again? It was I1 minus I2. Similar fashion, you can solve this problem by essentially simplifying this. You'd get them into that general form. You'd get them, it would be A times I1 times, or plus B times I2 plus C times I3, and it's equal to D. There we are. And so you'd have your 3 equations there. Are there any questions about this problem? Yeah?
With the 5 kilo ohm resistor.
Yes?
I thought the way we were taught to do it was to assign polarities to each resistor.
You can.
So why are the polarities different between equations 2 and 3?
Yeah.
For that one.
So there's 2 ways of doing it. You're absolutely right. Your lecturer might say that they want you to put down the polarities. And what that does, essentially, so I do this right here. A positive here and a negative here. When I'm doing my mesh currents, then I'll have to take into account which side of the resistor, or which polarity I'm entering through. So if you see I3 will be entering through this, the negative terminal. And so as a result, you would say the voltage across this would be negative, right? And then from the other side, from the I1, when we did this mesh, it would be positive. So the voltage would be positive. Now, if you don't use the polarities, you can sort of like ignore that. It's already sort of like accounted for, essentially. So there's 2 ways of doing it.
Can you show that it's the same as in the equation?
Yeah, I could definitely show that. So if I did essentially give this a polarity, so we'll just say that it's positive at the top, and for the we'll just do the super mesh first. So we'd see that from I3, as we're approaching this, let me do it in blue. So we've got this and this. We have I3 going this way. So we would come and we would look across here. What we would say is that this voltage, or the voltage running through this, would be I3 coming in through the negative, but it would be I1 minus it would be essentially I1 minus I2, because you're going through the negative terminal. And so in this case right here, this is the mesh current for the third equation, so this would be this. Because you're approaching that resistor from the top, you're going through the plus, so this would be positive. And so essentially these are the same. If I just distribute this negative, you just get what you got before. So it's just sort of like baking in, or just one way of doing it, essentially.
But the way you're saying to do it, which is probably easier, is just don't sign in polarities and then always make the resistance positive.
Yeah. So you just look at sort of like the net current going through it. If I say that I have this branch right here, and I've got this current going this way, and I've got this current going this way, if I know, or if I'm looking at the current, and I want to say that I'll take the net current as the one going in the direction minus the one going away from it, essentially. Hopefully that sort of cleared things up a bit. Right, so that problem's essentially done. I have this bonus problem. This doesn't come from a practice. This doesn't come from a past paper. And so it's a bit unique, but you've probably seen a question like this in maybe your textbook or maybe some other problems you've seen. This problem has two meshes, and it has two sources, as you can see. It's got a voltage source and a current source. And so your first inclination might be, mesh analysis or nodal analysis. What we can see, though, is that between these two meshes, or between these two so this is that first mesh and that second mesh, there is no wire through here. And so as a result, these meshes are essentially sort of isolated. So what this question really is, it isn't one mesh to be analyzed, it's two circuits independently. But they are sort of related, essentially because this current source depends on this current here. So you would analyze this circuit first, because this has nothing dependent on it. Right? You can answer this because you've got the independent voltage source. And you'd find the current, you'd find I/O, and then given this I/O, you can find the current going through this circuit and then solve this circuit. You solve this one after. So you do the left one and then you do the right one. And so that's the sort of workflow you think. You think, what can you find first? And then using that, what can I find after? So the question asks, we have to find and the power dissipated by the 8 ohm and 22 ohm resistor. So it'd be these two resistors and the voltage. So in order to look at the second circuit, we have to first look at the first circuit. So we'd have to look at this one first. So in order to do that, what we do, whoop, that is not what I wanted to do. There we are. What we could do is that we'd say that this is 10 volts. This right here is ground, so this is 0 volts. And so we can use this V equals IR. We know that the voltage across this would be 10 minus 0 volts, so this would be 10 volts. And so we could say that the current going through that 25 ohm resistor, so I25, is going to and so that would be just 10 on 25. As in, you can simplify that to be 0.5 amps. Now, we've solved this circuit, the left circuit, but we need to find the right circuit. Now, I/O is defined to be in the opposite direction to I25. We've defined that this is the positive side of the polarity, this is the negative, so the current would be going down through here. This is I25. But I/O is in the other direction. So we'd say that I/O is equal to negative 0.4 amps. That means that this current source is giving 5 times that, 5 times negative 0.4 amps. And that would be just 2. So it would be negative 2 amps. Essentially what this current source is actually doing is that it's pointing, but we'll just work with negatives instead. We have that, so we have the current going through or set by the current source, is negative 2 amps. And so what we can say is that it flows through this mesh. This would be negative 2 amps. This would be negative 2 amps. Now, as we can see here, this resistor is in parallel with this wire, and so this becomes a short circuit. And so we don't actually have a look at this. The current, this 2 amp, wouldn't split down here and here. It would just go down the short circuit, and there'd be no current going through the resistor. Yep.
The negative, like because it's.
Oh, did I have
the current source, because it's 5 times 10. What is it? Wouldn't it be negative 2.25, not negative 2?
negative 5 times 10 on 25
Yeah.
is 2.
Wouldn't it be?
Sorry, maybe I'm calculating it wrong.
Yeah, so it's like 0.5 instead of 0.4.
Oh, sorry. Where did I say that?
You mentioned it and then you wrote the correct thing.
Oh, sorry.
Oh, sorry.
I meant 0.5. So that'd be, this is just essentially, yeah, what am I doing here? This one was just from the previous one, and so this is 5 IO. It's just going to be 5 times negative 0.4. Write that down. Maybe I should write that down. No, it's right. My bad. And so what we can find is that we have to find the power dissipated by the resistors, and then we also have to find VO. VO is fairly straightforward. We can just use V equals IR. So we know that VO will be equal to, well, the funny thing is that we've defined the polarity here to be positive on this side and negative on that side. And so the current going through this resistor would be negative. So it's like a sort of like a double negative issue. So what we would have is that we would do negative IR. And we know that I is negative 2. So essentially, we get the negative of negative 2 times the resistance. Are there any questions for that? Another way you can sort of look at it is that instead of doing negative 2 amps that way, this way, you would do, you could do 2 amps this way. And so the 2 amps is going through the positive terminal, and then it just should give you a positive answer. And so that's the voltage. Oh, sorry, I wrote ohms. 16 volts. And so now we have to do the powers. So the power dissipated by the 8 ohm and the 22 ohm. Well, we know that the 22 ohm is actually bypassed by the short circuit. So the power through this will just be 0 because there's no current going through it. And so if P is equal to VI, if I is equal to 0, then P is equal to 0. Yep.
So like, did it not go through the resistor because the current
Around.
the least resistance?
Yep.
off?
Yep. And then we can find the power dissipated by the 8 ohm. We can calculate that, so that would just be P is equal to VI, but it's also equal to I squared R, where I is what we found earlier. The polarity actually doesn't matter because you're squaring the answer anyways. We'll just make it positive. So it would be 2 squared times 8. So it would be 4 times 8. And that's going to be 32, I believe, watts. And this would be dissipated because it's a resistor. Are there any problems with that? No? Yeah, well, this is that's the end of part section 2. Hand over to Otto to cover circuit theorems and
QR code, Can I get you guys to scan it and then just fill out attendance? That way we can, because we get money from ARC for running these events, and that way we can keep continuing to run these events. If everyone is able to just get their phones out ready, just so I can run around so you guys can scan this and just fill it out for me, please. Have you guys already filled it out? Has anyone not filled it out? Okay.
All right. Perfect. Thank you very much, Liam. And thank you super much, Blade. That was fantastic. All right. So, get around to that, and I will just get started. Little extra thing I want to clarify. Just over here, when we talk about short circuiting and then therefore no current passing, really just rely back on your current division resources, where basically you go, okay, what is my current divider between something that has 0 ohms and something that, sorry, that should be a line, something that has 0 ohms and something that over 0 plus 22, so that's going to have all the current. This one's going to have 0 over 22 plus 0, so no current. But yeah, good question. Just want to be a little finicky when we say current follows the path of least resistance, because, I mean, at this point, I feel like we should know that if this is 1 ohm and this is 2 ohm, there's current in both of them, right? If they're connected in parallel. So, fantastic stuff. Let's get moving. Circuit theorems. Let's do this. So, a couple of current points. We're going to be covering superposition, a little bit of source transform, Thevenin and Nodal equivalent circuits, and max power transfer. All right. And always, if you have any questions, raise your hand. You got this. And yeah, let's get on with it. So, Thevenin part 1. We're going to find the Thevenin equivalent voltage of this circuit as seen from the terminal diagram. So that's what we got there. We got A over here, B over there. So, let's quickly jot down that circuit. In your circuit diagrams, always just like make sure you get all the details, silly mistakes and all. Let's do this. So, what are we going to do? We have, that was odd, we have pretty much 3 or 4, geez, so many meshes. It's not the nicest. Oh, in this thing, I forgot to label this as I0. Anyways, so that's the question, right? We want to find the voltage between A and B. So this is the thing we want. Let's go ahead and try and find a way to find that. First things first, we see a sneaky parallel voltage with a resistor. So we're going to immediately go ahead and apply our source transformation. Fantastic. So what does the circuit become? A resistor and a... Never mind. Sorry. We can't apply source transformation here because that's voltage in parallel with a resistor. So yeah, wrong way. We can't do that. So no bueno on source transform. Alright? So we already know the voltage here. We're going to call this Vx equals 10. And now we got this over here. Now we can apply a source transform on this side, right? That might be a little bit more intuitive. So what does the source become? We transform those two in parallel to a voltage source and a resistor in series. So let's redraw the circuit. We get plus resistor, voltage source, resistor, and here are our terminals. Alright, let's make a little bit of a mess. And here we are. So that's 6K, my bad. This is 300. Oops. Alright. 10 volts, 100 ohms, 200 ohms, and 100 ohms here, and then 400 times I0. Let's not forget to label that. Alright, now, I mean, we already know the voltage here. It might just be easiest to find the voltage at this point. I like using Nodal in a more intuitive than currents, especially when you get slightly more convoluted circuits. So if I get to find the voltage between these 2 points here and here, then I can determine the current and I can be very happy. So let's try and do that. Let's do node at V1. Okay, so nodal V1, nodal analysis. We're going to find VAB. Let's do this. So what are the currents? I like to assume that all the currents are heading in to the thing. It doesn't really matter, but it just tells me which side of the circuit, which side of the equation I'm dealing with. So remember, sum in equals sum out in terms of the currents. Okay, so over here, what do I get? I'm going to call them going out. I lied. Going out means my voltage V1, right? And you'll see in just a sec, I get to start them with V1 minus something. So I get V1 minus 10 on 100. So that's the current going from V1 to this 10 volts right here, plus V1 on 200. Sorry, V1 minus 10 on 200, which is just the parallel to that, plus V1 minus, over here we have 400 I0 on 100, and that's going to be equal to 0. Now, let's just really quick determine what I0 is going to be. I0 equals, well, V equals IR. What's the voltage over it? It's going from left to right, so it's actually going from 10 to V1 over the 100 ohm resistor. Yep. So this is what I0 is. And so, what does this equation become? It just becomes a big something in terms of find I0 and then track my voltages around the circuit. How do we feel about that? Alright, let's do this. So we end up with V1, we group together, 1 on 100 plus 1 on 200 plus 1 on 100. What I'm going to do, just so that everyone gets a nice understanding, I'm going to chuck everything with V1 immediately inside it into this box here, and I'm going to throw the rest of the stuff that does not immediately have V1 in it on the other side. This 400 I1, I'm going to substitute and keep it over here. So I'm going to have minus 400 divided by 100, which is 4. I0 is 10 minus V1 on 100. And this is going to be equal to 10 on 100 plus 10 on 200. Alright, let's keep it going. Yes.
Is it meant to be 1 on 200 or is it 1 on 100?
Middle one. Are we talking about...
Yeah.
I'll just highlight it.
You took out V1.
Yeah. Oops. We're talking about this V1 minus 10, right?
Yeah, the bottom one. You see how there's 3?
Oh, yes. You're absolutely right. Thank you very much for pulling me up on that. I was a little ahead of myself. Good stuff. Alright. Let's do this. So, once again, grouping V1, we get, 2 over 100 plus 1 over 200. Wow. Let's do 5 over 200. And then we're going to drag this extra V1 that's in this equation over here inside as well. And so we add on 4 over 100 equals, now we're going to drag this 10 over 20 plus 40 over 100, that's about 4 over 10. Not much about that, but it is. So V1 equals to, actually I'll just group it all up together so it's nice and tidy. 13 over 200 equals to 5/10 makes a half, so 0.55, right? I believe. Yes, that makes sense. So V1 equals 200 times 0.55 all over 13. Fantastic stuff. Alright, but that's not the question. The question is to find Thevenin, right? And so, just keeping in this in mind, we've found V1. Fantastic stuff. That's not what we asked for. We're asking for VAB. Now, there's a couple ways to do this, and wow, it would be we don't. And so we've got to find an alternative method. The alternative method I'm going to think up is going on a little bit of a walk, right? Now that might sound a little bit funny, but I mean it in all honesty. Let's keep that as I0 and that as VB. Alright, I'm going to find not really this current, but I'm going to walk around my circuit as such to find VAB. Does that make sense? Is there a bit of an intuition there? Because really, this voltage to this voltage is the exact same as the summation of voltages going around the circuit, right? So let's do this. Let's do this. I'm going to go ahead and try and make as much mess as I possibly can, and I have VA minus 10. Sorry, what I'm going to do is I'm going to identify these little voltage walks I'm going to go on, right? So I'm going to say, okay, let's say VA equals 0. This is the assumption we've made by saying this voltage right here is going to be 10. So then I've gone from VA to my I called that Vx before. Vx as 10, and I'm going to V1. V1 we said was going to be equal to 200 times 0.55 all over 13. And now we need to find VB. Alright, now how do we find VB? Well, we've got a voltage here, we've got a source right here. We know what I0 can be because we just this here equation, and it should be pretty fine and dandy. Any questions about that kind of methods thus far? Fantastic. Let's do it. So, first things first, what is I0? I0 is equal to 10 minus this mess. Let's actually simplify what V1 is. Plug that into the calculator. 0.55 divided by 13. We get 8.46 over 13, which should give us about 0.118. Okay, so this is what I0 is, and so we say V1 goes down to here. So we need to what that current is going through. Okay, so we say 10 volts. Okay, what I'm going to do, just to be as nice as possible, is redraw the circuit just over here. Voltage source, resistor, two resistors, which I'm going to simplify, a resistor and another voltage source. Okay, I'm just trying to find my way from here, A to B. Okay, I've said that this one's 10. Now I need to find the current running through to this node, which was V1, and I know that the current in equals the current out. The current out is going to be going through here. So when I find this current, I can tell the voltage difference between V1 and this here V2. Okay? Minus VB. I know that's going to be equal to my 400 I0, but I need to know what V2 is, right? To find VB. So let's do this. The equivalent resistance of the 100 and 200 ohm resistors we have over here. We go ahead, we do our equation, 1 over 100, sorry, 1 over 1 over 100 plus 1 over 200, sums and products. So we get about 200 to become 20,000 over 300, I believe, yep, which is just going to be 200 on 3, okay? So that's the resistance there. So now we can set our REQ, which this one is going to be equal to V1 minus V2 on this resistor here, okay? And that is the 100 ohm resistor. So 100, okay? So moving forwards, we can say, rearrange to make V2 the subject. So we say V2 on 100 equals, shift everything over to the other side, V1 over 100 plus V1 on REQ plus, sorry, that's meant to be a minus 10 on REQ, okay? And we can go ahead and multiply everything by 100 to get V2 equals 2. Let's plug this into the calculator. 100 times, all right, V1, this value over here, this is V1, yep. So 100 times in a fraction, 8.46 on 100 plus 8.46 on REQ, which was this value, 2/3, so it becomes 66.67. So we do that, and then we're going to subtract 10 over that same value. Bam. We get V2 being 6.15 volts. Alright? Good stuff. Now, this means that VB is less than 6.15, right? So, we say VB equals 6.15 minus 400 I0. We plug in I0 once more. So we subtract 400 times I0. Remember, I0 is this value over here. It is in amps, 0.118. Bam. Which is going to be minus 41.05 volts. Alright? Now, is that the end of the question? Not quite, right? Typically, when we go VAB, we're using VA minus VB, right? So, we took this value to be 0, and this value is identified above. So VAB, our Thevenin, is actually going to be 41.05. The whole method that we worked through was being able to trace around the circuit and pretty much just accumulate our voltage as we went through. Was that alright? How do we feel about that? Okay, so now that we've found the Thevenin there, we're going to go ahead and try and find the Thevenin resistance. Now, that's going to be a little bit of a pain, but there are a couple tricks we can try and use. So, what we see right here is a voltage source, a dependent current source. Now, dependent and independent, they don't really mix, especially when it comes to Thevenin, so we've got to use methods 2 or 3. So let's have a quick run through of what those methods are. We hit method 1. Method 1 is we turn off the independent. Just simplify. Now, the condition for this is that you can only have independent sources, okay? Right? Now, you have your second method, which is we're going to go ahead and find Thevenin as well as I Norton, right? So Thevenin over I Norton, or as we might otherwise call it, I short circuit equals R Thevenin. Now, that's a method in its own. That is fantastic. However, it too has a condition, and the condition is not only dependent sources. That's not how you spell that word. Not only dependent sources, right? You need at least one independent source for that. And then we have method 3, which is our dummy source. We introduce a dummy source at the terminals A, B, and then we go ahead and do Thevenin over I short circuit. Rather, this is your voltage over the current of your dummy source, right? So we just use V dummy over I dummy equals R Thevenin, okay? And the condition for this is universal. Specific scenario, we would need to use it since it is such a pain in the butt to get through. You must use it for only dependent. Alright, good stuff. Now, moving forwards, with that in mind, we see a independent, we see a dependent, we have to use method 2. Let's get into this. So, we've calculated Thevenin already, so that's fantastic. Thevenin is known and is equal to, what is it equal to? It was 41 point, where did I write it? Here, 41.05. So, let's go ahead, write that down, 41.05 volts. Alright, now we just draw a straight line between those two, and we need to find the current. So this is I short circuit, it goes from A to B, right? Since we're using the same terminals as before. Now, some quick things that happen immediately to this circuit, let's go ahead and try and figure them out. We've introduced a short circuit. What we know about short circuits, it basically nullifies this here resistor, right? Got a short circuit running right over it, in fact. So we don't need to consider that. That is no longer existing anymore, all right? All right, what else can we do here? Well, we could go ahead, I'll introduce this I0 again. We could go ahead and just run it back, see, okay, we've got this voltage, maybe we can find this voltage using the exact same method. I0 here. Well, if I was taking VA to be 0, then in this new scenario, VB would be 0. And I look at the equations I've used that don't really care about what V and V, well, rather what VB is relative to VA, okay? And so you'll actually find that most of our working up until the introduction of the 40I0, saying that, oh, we're going to care about what VB is, we don't really mind at all, because we've only looked at things that don't touch A and B. We only looked at stuff that touches A, right? And so we can actually immediately carry forward and say that, oh, I know what this voltage is, and you're never going to guess. It's going to be our trusty 8.46 volts, right? That we've gone ahead and applied here. Did I say 8.46? Right? The important method we've applied here is just the understanding of, okay, let's hold on for a second and think about all the circuit elements that we've applied, right? Now, we might want to double check this and verify. So, let's go ahead and think of this. What is the method going to look like? We have a short circuit. We know the voltage here. We know the voltage is 10. We can go ahead and say, okay, current through this one equals current through this one, current through that one. Okay, hold on a second. I can do a source transformation here, and so it would just be the current through to my I0. Now, that doesn't touch B, and so I would get we can confidently say 4.86 volts right here. Now, the really cool thing is, we said 8.46 volts there. We get a current here. We get a current going up there. And therefore, we can determine a bit of nodal action right here, which would give us I short circuit. Yeah? So let's go ahead and look at this. We say that I short circuit is going to be equal to the current coming out. So that's going to be the current going over here, I'll call that I1, and the current coming through here, which we know is 4I0. So I say I1 plus 4I0. Okay? I0, I calculated previously. How did I calculate it? Well, I calculated it completely independent of my other circuit element. Two things touching A and not touching B. So that's the entire premise of this kind of using my previous resources again. It was very finicky, but it allowed for this step. So we look at this garbled mess that we made. Sorry, I won't include you. Yours is probably so much neater. And so I0 we go ahead and we take as 0.118 amps. Fantastic. So equals I1 plus 4 times 0.118 amps. Now what was I1? Can we calculate this? Well, since we've gone ahead and short-circuited A and B, we know that, okay, let's take VA as being 0 volts. We know what this is in voltage. So just going to be 0 minus 8.46. So this is the voltage over this resistor when I assign it this polarity, divided by its nominal resistance, which is 100. Okay? And let's simplify this. 4 times 0.118, 0.472. And what do we get in total? Let's double check. We get 0.3874. Fantastic! We found I short circuit. And it was without really needing to do any bonus big equations. It was all about a little extra analysis on our end of, okay, what can we carry forward? Sorry, what can we carry A and VB, right? So nodes A and B. So let's go ahead, we bring this over here, and we say R Thevenin equals V Thevenin over I short circuit using method 2. We'll just wait for it to register. And yeah, lovely stuff. Do we have any questions about this somewhat tedious use of the equations? Alright, looking fantastic. Let's keep it moving. So that's 0.3874, which would be about 106 ohms. Don't know why there's a point there. Alright, about 106 ohms. Alright, fantastic stuff. And take the maximum power transfer of this one. Now, if we remember the little formula that we flashed you earlier, we say for maximum power transfer, the load resistance equals Thevenin resistance, right? No need to complicate things just yet. That'll happen later in the course, don't you worry. And then we need to talk about max power transfer as well, which we can just do V Thevenin squared over 4 R Thevenin squared. Now, there's actually a really easy way to derive this, in case you forget. And really, just think about your equivalent circuit. Okay? We've gone ahead and said, out of the blue, okay, max power transfer, it happens when RL equals R Thevenin. Who knows, maybe you did a math assignment on this. But you have RL. They're the same, maybe they're both R Thevenins. Let's label them R Thevenins, just for the sake of it. Just so that we get this extra intuition. voltage divider, and oh my gosh, what's the voltage right here? It's just going to be a half, right? Because, you know, we have the entire resistive load, we're only talking about the voltage over half of it, it's going to be half the total voltage. So Thevenin on 2, so V squared on R equals power equals V Thevenin on 2 all squared times 1 over R equals, you know, V Thevenin squared on 4R. Okay? Thevenin. Whoops. Alright, so with that out of the way, let's go ahead and determine, first of all, what load resistance. It would be about 106 ohms, which is our R Thevenin. So we say RL is that. Fantastic stuff. We take our free marks when we can, and then we move on with the maximum power that can be transferred. So we say P max equals V Thevenin R Thevenin, which equals what was it, 41.06? Was it 605 on 4 times 106, and don't forget the square. Alright, and bam, we get about 3.97 watts. Alright, now that is actually a pretty high number in terms of power, just when you start talking about certain resistances, you know, inversely proportional, all that jazz. But yeah, good stuff. Any questions thus far? So, superposition, let's do this. We have something of a devious circuit here. It has 4 sources, also we think. Now the reason I say that is because this question and a few others were made by yours truthfully with a little trick in hand. Now, what is the trick here? Well, the trick is that, are there really 4 sources? Let's think about this. We know that when we do superposition, we turn off all the other sources, and this is regularly only applicable to when you have independent sources, right? And it just makes our circuit analysis a little bit easier in certain circumstances. So, as per usual, we're going to mark these sources 1, 2, 3, and 4. And with this in mind, we're going to read the question. It asks us to determine. Alright. Now, with power absorbed, there are a few things we got to do. Now, first question is, can we superposition or superimpose power? Now, something you might have seen in your lecture slides is that superposition only works with linear factors within your circuit, okay? Linear variables, okay? And we'll actually go through and think to ourselves, here's a resistor, maybe here's a current source, maybe here's a current source, okay? And they both go ahead straight into the resistor, right? So, oh my gosh, there's all this current going through. If I go ahead and apply superposition here, then I hide this one. I'll call this I2, I'm going to call this R, okay? And I want to determine what is the power of R, okay? So, power of R in this first superposition is going to be equal to I1 squared times R. Fantastic. The power, I keep on mixing up my P's and my R's. Oh my gosh. Alright, P R2 is now I'm considering what is going to be highlighted. And what do I get? I just get I2 squared R. But when I consider them together, right, as I typically would, because who really needs superposition for this kind of circuit? We say I1 plus I2 is the current going through that resistor. It gets squared and times. here is that these two things, when added together, they do not equal, right? They do not equal this total that we've calculated. And so, the reason is, as I said before, superposition is only for the interaction of linear variables. So our voltage is linear, our current is linear, our power is not. Our power is, if I just look at the power equation, it moves with the variation of a square. That's not linear, okay? So, to determine the power absorbed by the Vx resistor, I need to determine what Vx is, right? So that's the trick we need to apply. So, let's get on with it. We're going to redraw the circuit a bunch of times. So let's just begin with circuit drawing, okay? We're just going to use circuit 1 right now, okay? Source 1 right now. So everything else gets turned off. I go ahead. Source 1 is my 2 amps. So I draw my 2 amps. Bam. I get my resistor. I keep on drawing. Now, usually I'd have a source here. I'm just going to do the entire drawing for now, just so we can reuse it for later. So, this is the entire drawing. I'm just going to go ahead and copy it so that I can go ahead and modify it at a later time. Alright? So, here's our drawing. Alright, if I'm only considering source 1, what does that mean? I turn off everything else, and so this becomes a short circuit, this becomes a short circuit, voltage sources become short circuits, and current sources become open circuits. Okay? So when we do this, we actually get something a little bit nicer, I would say. So we're still trying to find Vx here. We're only considering this source. So these two become series. Then these two also series, and yada yada. Okay? So we break it down and we simplify. Okay? So as I said before, I'm just going to drawings first. So we paste it again, we get drawing. So this is using source 2. Source 2 is our 5 volt source. This is the only one we're considering, and so we go ahead and turn off everything else. Alright, good stuff. There's a little funny thing with this one, which you might be able to find on your own. But we're going to keep moving forwards. We do circuit 3. Keep that in red. We paste. Alright. Source 3 is the other voltage supply. So we turn off everything else apart from it. And then we have source 4. Alright, source 4 is this other current source, so everything else turns off, and there we have it. Alright, so there might be some tricks we rather immediately see, and let's go ahead and think about what else turns off in these circuits. We look at the first circuit, and really nothing else except for this here resistor has no current going through it, right? So we know that that resistor has no current going through it because one of its nodes just got detached from the circuit. It's now hanging open circuited, no current, right? So we don't need to consider it, especially because it is not important to our value Vx, okay? We look at circuit 2. Well, this has been open circuited, as we mentioned. So this has no current. Then our source also has no current. If the source has no current going through it, sure, we can go ahead and, this was a 5 volt source, we might be able to call this 0 volts at the bottom, but there's no current going through it. Yeah? And since there's no current going through it, there's no current going through the rest of the circuit. There's nothing else being entered. And so, while this might be 5 volts, this would also be 5 volts. Mind you, because this top current source is also turned off, that's open circuited, that's open circuited, so touching nothing, they don't care. Well, we don't care about them. This would be 5 volts, and this would be 5 volts. Everything becomes 5 volts in circuit 2. So there's actually no voltage difference over Vx, which is it's a little strange, right? But hey, we have our fun. Nothing. Rather, the source, the 5 volt source we have right here, contributes nothing. Which sometimes you get goofy circuits like that. So let's go ahead and look at circuit 3. Likewise, we have an open circuit on both of our current sources. So we can go and say, okay, this resistor, it's hanging open, there's nothing going through it. Likewise. And hey, likewise. Now it's just this one mesh for that circuit, which is very cool. Since you just have that one mesh with the one voltage source, we can probably go ahead and perform a voltage divider. Fantastic stuff. We'll look at circuit 4. We're just looking at this bottom current source. Source is turned off, so no current running through these. We go ahead and play the same logic, and yeah, good stuff. Alright, and the method we would use for this, it's likely going to be another current divider, funnily enough. So the reason I say that is we're looking at this one big node, okay? This is one huge node. And it's important to identify those, especially when you turn off sources, because it can make simplifying our circuit so much easier. The current going into here is given by the source. It exits this way, or this way, or this way. Now, mind you, these form their own kind of mesh, so through there. Now, what does that mean? Well, it means that they cancel out. So we actually don't really know that much about this side of the circuit. In fact, you could redraw this circuit, number 4 that is, as, okay, we have a current source, fantastic. We have a resistor, and that goes over here. Now, we're going to separate it, and we're going to have a resistor. Oh, let's not do that. A resistor, and a resistor. Now, if you recall from earlier, this is just 2 different circuits, right? There's only really one wire, or rather one node, connecting them. And so, by our conservation of current, actually I think it's conservation of charge that we use for this. But anyways, you can tell that, oh, wait, this is 2 completely different meshes. And this mesh over here has no voltage source, and therefore is dead. And so, circuit 4 actually has no contribution. How crazy is that? So it's looking at these from, okay, when we break down in superposition, it can really simplify our analysis if we don't get too hung up on stuff. So we're left with a simple voltage divider and this mess over here, which we can go ahead and just use 2 meshes, I believe. The reason that we can use 2 meshes in here is because there is a voltage over this resistance, right? And that's where you get more current, you get a current actually do this. Let's label our resistor values and do this. So we got a 50 ohm, we got a 40 ohm, we got a 2 amps, we got 1 kilo ohm, 500 ohm, 1 kilo ohm, and a 500 ohm. Alright? And then for circuit number 3, we're just using the 500, 1K, and 500. Alright. So, and what was that voltage? It was 10 volts. Alright, so we say Vx1 is going to be the one on the left, that's Vx1, and the one on the right we can call Vx2. Alright, so now we're actually going to go ahead and analyze these circuits using our previous methods. So we've got 2 amps over there. We don't know what this is though. We're going to call this Ix. Alright? So let's go ahead and do this. We say there are 2 amps until we get to here. So we really only need to use this one mesh equation with Ix. Right? So we say, first of all, the 500 ohm resistor. If we follow the direction of Ix, this is using the other, I guess, mesh trick that we used before, rather than assigning polarities. 500 Ix minus 2, which is my other mesh current, plus 1K Ix plus 500 Ix equals 0, right? And so now I can just rearrange this for Ix, and I know that this value right here is Vx1. Okay? Let's do it. So we have Ix equals 1000. Ix equals, actually, I can immediately go ahead and calculate 1000 Ix. So I don't even need to know what Ix on its own is. So 1K Ix equals Vx1 equals 500 volts, which is rather insane. And that's purely because we got current sources. Current sources are a little bit broken. So that is Vx equals 500 volts. That's x1. Okay, now we need to calculate Vx2. So superposition, now we're doing our voltage divider, and we can actually go ahead and pretty much group these two resistors together because we're only considering one loop, and the same current goes through all of them. Okay, so voltage divider, we say Vx2 equals that one's a resistor, so the resistor over the Vx2, which is the 1K, over the total resistance, which is 2000, 2K, right? Which gives us 5 volts. Okay, it's a little less grandiose than the 500. So in total we get Vx equals 505 volts. So now we go ahead and determine the power. So you say power equals, just go ahead and write that. V squared on R equals 505 squared on 1K. We're going to get a massive number, which will be 255.025 watts. Fantastic stuff. All right. Just thrown at you one by one in these circuits. We're going to get on to capacitors. All right. Now, a little spoiler is that I've made a question. Not this one. This one is from last year's paper. Very useful. I've made this little bonus question. Okay. Something to look forward to. And it's all about diodes because thanks to Felipe, we know what to target, right? But mind you, this is not to say that this is an executive, okay, everything we say in this crash course is gospel. We're just going to try and best prepare you given the feedback that Felipe has given us. Okay, so let's do this. Current capacitors, here are our content points, part 4. Alright, important theory, steady state. What does steady state mean? It means a long time has passed, typically, and so everything is DC. long time passed. So that means that there are no outstanding changes ongoing in that circuit. Yeah, we've got natural responses, which are typically capacitor discharges. So that's when maybe we flick a switch and then, oh, there is no longer a voltage source. I have to release all the voltage the capacitor has stored up. We have a forced response, which is, oh, we flick the switch back, it's charging back up, typically. Okay, so capacitor sees voltage source. And then quite generally, we have our equation, which VC at a long time has passed. That's what it's going to end up being. VC0 is our initial condition, which you will typically always be told, whether that's a previous steady state or another change. And then we have our time constant here. Okay, so time constant is your R Thevenin as seen by the capacitor. So you take your capacitor's terminals and you find your R Thevenin seen by those when you exclude the capacitor, right? So capacitor in these analyses would be treated like the open circuit between A and B, okay? So let's do this. 2024 term 1 question 5. This one was I think it was 22 marks in total. We can count that. You can count that up in your own time, but that's just me trying to remember. But anyways, let's get on with it. The circuit, both switch A and switch B initially open for a long time. Okay, so what is that telling us? It's telling us initially the circuit was, mind you, with these capacitor questions, you always want to go ahead and define your circuits for each time instant. Okay, so circuits have been open for a while. Sorry, switches have been open for a while. So these are the only things we need to consider. All right, this is 2 microfarads. This is 60 kilo ohms, 30 kilo ohms, 10 kilo ohms. Okay, so this is what the capacitor has been exposed to for a long time. Okay, now we're going to calculate the voltage over the capacitor when a switch is closed. Just one of the switches. Okay, the switch is going to be this one. So in other words, this switch will become this section will become a short circuit, right? And so short circuit around a resistor, we no longer, that resistor is kind of excluded from the system now, right? No current goes through it. We can wipe it out from our circuit diagram. So first things first, let's go ahead and determine VC0, okay? Because it said steady state for a long time, it means this capacitor has built up some charge. So long time means, DC, capacitor is open circuited. So we just perform a voltage division over this 60 kilo ohm. Does that make sense? If it does, please nod your head, because that is correct. Let's do that. Okay, so voltage division, we got 12 volt, we got 10 kilo ohm, 30 kilo ohm, 60 kilo ohm. So we say voltage division. VC, mind you, this here is VC. VC0 equals our total. Wait a minute, I think when I was doing a voltage division over here, I said something goofy. But anyways, back to the point, let's not get distracted. 12 volts times 60 kilo ohms over 100 kilo ohms total. That's really nice. So we take 6/10, 3/5 of 12. That would be 3.6 volts, I believe. All good? I think I...
Or something. Did you not say?
Oh, that's after the switch is closed, right?
Okay.
So that's going to be later.
Okay.
I think this right here is wrong because I can't do math. I was meant to times by 6, so it's meant to be 7.2 volts. Please do bring me up on these things. So, let's keep going. At 0. Now, mind you, with these equations, you're given that your capacitor equation is I equals C dV on dt, and this is all relative to your capacitor here with the rating C. This is the voltage, and from top to bottom, this is our current, okay? So capacitor and current, top to bottom. So if I push current through a capacitor, it increases in voltage, right? And that's just how it goes. We can go ahead and, if we really feel like it, do a differential equation to calculate these things, but for the sake of this course, that won't be necessary. It gets more complicated the more you do that, which is later year courses. Let's do that later. For now, let's just stick to our general equation. And we exponentially decay towards our steady state at infinity, okay? Let's do this. So that's VC0. Now let's find out what our steady state is, okay? What is VC infinite? Well, actually, it's not VC infinite. I mean, it would be VC infinite if we consider, okay, what would it be going towards? Now this is the tricky part of the question. We know that the switch is only turned on for 0.1, well, yeah, it's turned on forever, but we're only analyzing between 0 and 0.1, right? So we can imagine the circuit as though, between times 0 and 0.1, as though that switch would stay on forever, and we're only thinking of that switch. So the circuit doesn't know that we're going to flick another switch in 0.1 seconds, yeah? VC infinite, we use the circuit with this short circuit. Short circuit means the 10 kilo ohm resistor that was previously there, which is stubbornly not rubbing out, doesn't exist anymore, pretty much, right? And so we need to redo our voltage division, yeah? So 12 times 60k over 90k, which is 30k plus 60k. Let's do this. 2/3 should give us 8 volts. So we know that it's going to try to charge up towards 8 volts. Holding on all good? Alright. So if it were left alone, we have our voltage time graph. It's been sitting at up to there, it's all happy. And then right here, where I'm going to say 0 time, it's going to try and jump up towards an asymptote towards 8 volts. Yeah? That all good? Alright, fantastic. Now, we're missing one last thing from this equation, and that is our time constant, okay? Tau. Now, little bonus thing, typically we say 5 tau is, okay, you've pretty much reached where you were going, because that is equivalent to, it's like 5 decay constants, so don't worry too much about that. 5 tau, 5 times your time constant, is when you've hit steady state, pretty much, okay? So, we go ahead, what is tau? Tau equals Thevenin times C. We're looking at, I'll just highlight them. Oh, that's not the highlighter. There's the highlighter. We're looking at these two nodes and determining the Thevenin equivalent. So we look at it, we get a 60 kilo ohm resistor, but also because we're considering Thevenin equivalents, we can turn off this 12 volt source and say that the 30 kilo ohm resistor is in parallel. Is that all good? All right, fantastic. So 30 kilo ohm parallel 60, I think it's 20, and it should be 20. So let's doubt myself and check. All right, because no harm in checking. Product over sum. Fantastic, it is 20. So 20, mind you, that's a kilo ohm times microfarads, which is going to give us 40 times 10 to the 3 times 10 to the 6. Sorry, minus 6. 4 times 10 to the minus 2, which is 40 milliseconds, right? Yes. So this is our time constant. Now we can just chuck it into the general equation. So we say for t is between 0 and 0.1 seconds, VCT equals V infinite. So this is V infinite, so VC infinite, which is going to be 8 volts minus, we say once again VC infinite, 8 minus VC 0, which is we're going from 0 to a 0.1 time, so we say just minus t. We're starting at t0, which is just 0 over tau, and tau is going to be 0.04, okay? And this will be volts. Now how can we double check this, like dummy check this? We go ahead, plug in time is 0, okay? We plug in time is 0, e to the 0 is 1, 8 minus 8 is 0, 0 minus minus 7.2 is 7.2. That was my steady state beforehand. I dummy check again, t goes to infinite, e to the minus infinite is 0, I'm left with 8. Very happy there, okay? So this is all done. Now, the second switch is closed. Actually, yeah, so that was part. Alright, energy stored in the capacitor. Do we have our equation for that? Does anyone recall the equation? Do you guys? Do you live?
Isn't it half C V squared?
Exactly. Alright. It should be. Please do fact check me. It should be half C V squared. That's tucked away somewhere in my memory. And I'll try not to forget it. So, this equals energy in a capacitor, right? And so, we need to find, okay, 0.06 seconds. We can use the equation as before because that's between 0 and 0.1 seconds. So, we plug it in. We go back over here. We say, okay, what is VC at 0.06, right? And so, into our equation, we say 8 minus 0.8 times e to the power of minus 0.06 on 0.04. Now, you'll find that 0.06 is about 1.5 tau, and so it'll be, it might even be like halfway there, right? So what we get in the calculator is 7.82. The reason I mentioned that just now was dummy check. You see, okay, how many tau is it? If it's close to 5 tau, it should be very close to 8, yeah? So 7.82 volts. We can run back over here. So I say EC equals a half of 2 microfarads. So that's 2 times 10 to the minus, which should give us, I'll just square this number, 6.118 times 10 to the minus 5. It won't be watts because we're talking about energy, not power. So it should be in joules, correct. And you could put this in terms of microjoules, but all the same, we're very happy. All right, fantastic stuff. Now, the second switch is turned on. Here is now a little bit tricky because what do we take as VC? 0, or like 0, okay? It would be VC 0.1, yeah? We need to take what this would be at 0.1. So let's just very quickly calculate that. VC 0.1 is going to be equal to, let's go up to our calculator. Hopefully it still has stored the equation. 0.1, which is 2.5 tau, which will be 9.734 volts. Okay? And we need to change the circuit. Now, that switch actually isolates our voltage source. Okay? It brings that end down to 0, down to ground, and we have, I'll just draw on this. It now looks like this. Okay? So we don't need to think about anything on the left-hand side of the circuit because that switch is closed. Okay? It short circuits through there. That circuit acts on its own, which will also short circuit. Nothing goes through to this right-hand side. Now, if it were just a regular DC circuit, we laugh at this and we say, oh, everything's 0 now. But we have a capacitor there. That capacitor has stored charge. Voltage that it has accumulated via that charge is going to be our power source pretty much. Okay, it will discharge now. So, once again, we looked at our steady states, so we can say VC infinite. Actually, I'll just move this down a bit. Oh boy. Alright. Bam. So, VC infinite is going to be equal to 0 because there's no existing voltage over it. There's no V Thevenin for it. Now, VC 0.1. This is like our initial that we're going to use. We calculated this before as 7.934 volts. And tau. Does tau change? What do you guys reckon? I reckon it stays exactly. But all the resistors in our circuit that we were analyzing previously are still there. And that's the 30 kilo ohm and 60 kilo ohm. Yeah? So, our tau constant stays the exact same. 0.04 seconds as previously. Now, mind you, there may be some sticky scenarios where that tau constant changes. Maybe in the future, maybe in the near future. But, yeah. Let's do this. So we can just say VC T for tau is going to be equal to V infinite, which is 0. And then I do, it is meant to be a minus here. V infinite, which is 0, minus VC 0.7934 E to the minus. Now, here's the trick. Here's the trick. What is our time in this? The time is time counted from 0, not time counted from 0.1. So, we need to go ahead and act as though time is continued beforehand, right? So, let's think of this. Usually we would just put 0.04 as though it were usual. But we want e to the 0 at t equals 0.1. Yeah? So when t is 0.1, I want this thing to be 0. Okay? So we do minus 0.1 in the numerator. Hoped to mitigate, right? Which is this. You have your minus t0. Okay? So, fantastic stuff. Let's keep on moving. Alright, so here we are. We got our equation, and it's important to note that this is for t is an element of 0.1 to infinity. Now, I can also go ahead and simplify this to just 7.934 e to the minus t minus 0.1 all over 0.04, just for the sake of being neat. But let's keep on moving. Question 4. Alright, now we're going to also try and calculate the current flowing through the 30 kilo ohm resistor. Now this becomes a little bit more tedious. And let's go ahead and do this. Double check. 30 kilo ohm resistor, the one right here. Now, we have IC, we have I60, and we have I30. Now, let's go ahead and think about this. They've actually defined it as I0t, okay? So we're going to double check what the question asked of us. It wants I0t, okay? So we're going to say that that current is going into the node, okay? And so we can actually just perform our nodal equation right there, okay? So we go ahead and write it out. Be 1 immediately, okay? So we say that IC, that's going out of the node, plus I60 ohm, which is going out of the node, is equal to I0t, which is the 30 kilo ohm. That should also be okay. Alright, so what do we know? We can actually put these in terms of VC. So we have IC is C dV on dt, so we say C dVC T on dt, plus the 60 ohm, we just have the voltage going down to 0, so that's going to be VC T on 60, okay, equals, between both of these intervals, we can just go ahead and calculate this, right? I guess in the interest of time, actually, no, I'm just going to do it. Let's just do it. Oh, interest of time is so appealing though. Okay, so typically we would not like this equation, but the trick is we've already calculated what VCT is, and since we already know what VCT is, we can just take the derivative of it, right? And so this C dV C on dt, when you have your general form of VC infinite, I'll keep the negative in front just because I find it more appealing. Minus, in brackets, VC infinite minus VC 0 e to the minus t on tau. Derivative, so d on dt. What does this become? Well, it just changes, it just affects this, right? So we keep everything in the coefficient, we reject this, so this one gets crossed off. So we say VC infinite minus VC 0 stays in its brackets as the coefficient, and we differentiate. So differentiate, we multiply by the power of the exponential. So 1 over tau e to the minus t on tau. Alright? This is what we get from the derivative, and I'll leave the rest as a little bit of an exercise to you guys, just because we have run a little bit over time. So, with that, you can substitute this value, original thing divided by 60k, and that is your current going through that 30 kilo ohm resistor, right? Which, that's just a bit of extra algebra, yeah? You guys got this. Now we're going to do some diode capacitor funny business. So, something we haven't touched too much on today is the fact that the diode is and can be treated as an independent voltage source when it's on, right? So, with that in mind, let's go ahead and take a shot at this question. We're going to try and find what tau is when the switch is closed, right? So switch is closed, it's like that, we got a voltage source there, let's see what's going on. So let's think about whether this has been on for a while or whatever. Let's say it's been some current going through here. We got some current flowing through the entire thing. After a long time, this here is an open circuit, right? And so we redraw the circuit. This here we get 12 volts. We get our 300 ohm. Diode 1, diode 2, and 50 ohm. These diodes are rated with a 1.7 volts. So let's go ahead and think about this. In total, what is the current? Well, we got a single mesh here. Let's just run around the mesh and have our fun. So we say minus 12 plus 300 I1. Now, like I said, these are acting as independent voltage sources. They drop when we go through them, so they are facing this way. Alright? 1.7 plus 1.7 plus 50 I1. Okay? Now mind you, because all these things look like they're in series, it doesn't really matter which order I put everything. The same current is going through it. Okay? So this much equals 0. So I can say I1 equals to, actually I'll just group it up, 350 I1 equals to, I think it's going to be 8.6, but I can double check that. 12 minus 3.4, 8.6, bam. Alright, I0 equals 2. This number divided by 350, which, funnily enough, 0.0246 amps. Now that is what you might typically see because it is below, right? So that's actually fantastic. I can tell both of these are forward biased because there's actually a current going through it when I assume it on, right? And it's a valid current. If this current that I calculated here was like negative, or it was like either absurdly small or too big, I would then have to reanalyze my circuit to see if the diodes would behave differently. Yes? So the checklist is analyze, oops, what was that? I'll just write it again. If on, check if valid. If it's not, then we say otherwise, check off. We've done this, and we say there's a current flowing through here. So none of these are off. Neither of the diodes are off. Okay? They're both on. And so we can go ahead and reanalyze this circuit to determine the time constant. And the way it looks right now is we go ahead, let me just neaten this up a bit, plus minus, we got that. We have a voltage source, we have the capacitor terminals, we have another voltage source, and we get a resistor. Now, I might say that, in a little spoiler, this system somewhat resembles a battery, okay? And you'll see that in a little bit, but let's think about it right now. We got terminals A and we got terminals B. My circuit, and I'm trying to find my time constant. Remember, time constant equals RC, sorry, R Thevenin C. Can we easily find R Thevenin? Well, I just resort back to method 1, right? I can just short circuit these and then equate my resistances. So this is a really good example because it gets you to look at how the diode is an independent voltage source under certain conditions, right? And so I can say this is going to be equal to the parallel of 350, so that's products over sums, which is 300 on 7 times C, which is 5, which is 1500 on 7. I'm not going to bother simplifying that. Seconds, which is, mind you, because I've said the capacitance is 5 farads. If you see anything that says it's 5 farads rated, please do run. You are likely in danger. Just because the capacitance is so big, it's likely going to store tons of energy, which is why it's similar to a battery, maybe a car battery. Anyways, so the switch is left closed for a long time before T0, where it is opened. Determine VCT for T greater than 0. So let's think of this. It's left closed for a long time. We need to calculate what the initial voltage was. Okay, so we have our circuit over here. We're just going to be looking at that for VC0. Okay, which is just going to be this voltage right here. Okay, so it's including one of the diodes and the 50 ohm resistor. Sum that up because we know what the current was. Okay, how fortunate. 1.7 volts plus, because they're in series and we're counting it plus minus plus minus. This current, which I think I erased from my calculator, but I can get that back really quickly. Bam. This current times by 50, which will give us 1.229 volts. Okay, so VC0 is approximately just 2.93 volts. Okay, fantastic. Now, it's discharging, right? The switch opens. Where is current going? We have to reanalyze the circuit. So I'm going to redraw the circuit. Diode 1, capacitor, diode 2, resistor. Okay, the switch opens, so that bit is cut off. If this is cut off, then this voltage source is completely disconnected. We don't care about it. It also means that there's 0 amps flowing through here because it's an open circuit. We've said this a lot, but it's because it's something interesting that happens. It also means there's 0 amps running through this. In other words, since there's 0 amps, there's actually a 0 voltage difference between there and here. If there's 0 volts, this diode turns off, right? It is not in forward bias, right? And that changes our circuit again. So I'm going to redraw the circuit. We get this. Now, the question is this diode in forward bias? What do we reckon? I reckon we have a voltage here, VC. I'm going to put an imaginary ground there. I'm going to call this 0 volts. And we have a voltage here, VA. Now, if we discharge this capacitor, there's a little bit of an intuition here. I know that VA will slowly fall towards 0 volts, but what will happen to the diode? So we let time go into infinity. This diode will remain in forward bias, 1.7 volts, and it will continue 1.7 volts as VC decreases, right? So what does VC approach? We actually see that IC equals 0, so that's what defines our steady state. So VA equals 0, so C does not equal 0, sorry. Equals VA plus 1.7 equals 1.7 volts. How strange is that? The capacitor discharges to 1.7 volts because the diode is so stubborn, right? Because if the diode were to turn off, the capacitor is just isolated. It stays at that thing, the current goes nowhere, which is another steady state, right? So we think about this, and we're going to discharge as such. So we know that VC infinite equals 1.7 volts. Now what about the time constant? first forward biased resistor is turned off. Does this mean we can no longer see the 300 ohm resistor? Yes, we cannot see it anymore. And so we need to reanalyze this circuit for our time constant. So this equals R Thevenin times C. What does R Thevenin become? Well, when we analyze it, we turn off the independent sources we can see, and we just get 50 ohms, right? 50 ohms is R Thevenin, 5 is our capacitance, so we get 250. We have a different time constant. And now we can just go ahead and plug it in. Okay? So we say V, C, T, this is for T being between 0 and infinity, rather T greater than 2, V infinite, which is 1.7, minus V infinite, minus, V infinite minus V initial, which was 2.93, e to the minus t on 250. And there we go. Sometimes you may wish to simplify this internal voltage, just the V infinite minus V initial. But yeah, there we have it. Thank you guys very much for coming. Hope you guys learned lots and had quite a riveting time with some of these bonus diode questions. And yeah, best of luck to your studies. And I guess for Thevenin assistance, we do have another recording that's already been recorded and streamed on our YouTube. You can access that at any time. It's all recorded. It's 15 Thevenin questions where we run through each of the three methods. So we did that. There's plenty of help there. And subcommunity recruitment, we expect to close early week 5 if you're still interested. 8 hours, really? Wow, okay. 8 hours until it closes. Do apply if you're interested. We have a lot of fun doing this thing, and we would like for you to enjoy it as well. This is from the academics portfolio, and we're just about ready to close. So let's